Naval aviation is defined by a continuous quest to launch heavier aircraft more rapidly and with greater safety. At the very center of this evolutionary arc sits the Kitty Hawk class of aircraft carriers. These massive vessels were the ultimate conventionally powered aircraft carrier in the US Navy, serving as the bridge between the dawn of the supercarrier era and nuclear propulsion. To understand the Kitty Hawk class is to understand the strategic realities of the United States Navy during the height of the Cold War, a period where technological ambition frequently collided with harsh fiscal and military realities. These ships were born from the hard-learned lessons of their immediate predecessors and lived long enough to launch aircraft into the skies over Iraq in the early 21st century. The story of the Kitty Hawk class begins with the Forrestal class, which holds the distinction of being the first true supercarriers. Commissioned in the 1950s, the 4 ships of the Forrestal class integrated the 3 great British innovations of post-war naval aviation. These were the angled flight deck, the steam catapult, and the mirror landing aid. However, the Forrestal class was effectively a first draft. As the ships entered service, naval aviators and flight deck crews quickly discovered significant operational bottlenecks. The most glaring issue was the placement of the aircraft elevators. On the Forrestal class, the portside elevator was located at the forward end of the angled landing area. This meant that whenever an aircraft was recovering and landing on the deck, that elevator cannot be safely used. Furthermore, the starboard elevators were positioned in a way that interfered with the flow of aircraft moving from the hangar bay to the forward catapult. In the high-stakes environments of carrier operations, where seconds dictates the launch tempo of a strike package, these design flaws need to be addressed. The Kitty Hawk class was conceived as the direct successor to the Forrestal class, designed specifically to rectify these deck geometry issues and optimize the launch and recovery cycle. The fundamental change was the radical reorganization of the aircraft elevators. On the Kitty Hawk class, 2 elevators were placed forward of the island superstructure on the starboard side, and 1 was placed aft of the island. The single portside elevator was moved far aft, completely clear of the angled landing deck. The relatively simple shift substantially improved flight operations. It allowed the ship to launch and recover aircraft with far less risk of deck collisions. Aircraft could be brought up from the hangar deck, fueled, armed, and moved to the catapults in a continuous, uninterrupted flow. To accommodate this new elevator arrangement, the island superstructure itself was moved further aft compared to the Forrestal class. These design improvements were taking shape against the intense backdrop of the mid-Cold War. In the late 1950s and early 1960s, the geopolitical environment was fraught with tension. The Soviet Union was aggressively expanding its maritime capabilities, focusing heavily on a massive fleet of attack submarines and long-range land-based naval aviation armed with heavy anti-ship missiles. The United States Navy was tasked with an enormous global endeavor. It had to maintain a persistent, visible, and overwhelming presence in the Mediterranean Sea, the North Atlantic, and the Western Pacific simultaneously. The doctrine of the era dictated that the aircraft carrier was the primary instrument of American conventional deterrence and power projection. The strategic requirements for sheer numbers of flight decks directly influenced the most fascinating aspects of the Kitty Hawk class history, which is the fact that they were built at all. To the modern observer, the procurement timeline of the United States Navy in this era seemed counterintuitive. The USS Enterprise, the world's first nuclear-powered aircraft carrier, was ordered in 1957 and commissioned in 1961. It was an absolute triumph of engineering, utilizing 8 A2W pressurized water reactors to achieve theoretically unlimited range and high sustained speeds without the need for constant refueling. Yet, the Navy continued to build the conventionally powered Kitty Hawk class well after the Enterprise was ordered. The USS Constellation was laid down in 1957, the USS America in 1961, and the USS John F. Kennedy in 1964. The explanation for this continuation of conventional power, despite the existence of the nuclear alternative, is rooted deeply in economics, industrial capacity, and the fierce bureaucratic battles within the Pentagon. The USS Enterprise, for all its revolutionary capability, induced massive sticker shock. The cost of building the Enterprise was staggeringly high, eventually totaling more than double the cost of a contemporary conventional carrier. At the time, the Navy was under immense pressure to maintain a fleet of at least 15 deployable attack carriers to meet its global commitment. If the Navy committed exclusively to nuclear power in the early 1960s, the defense budget would only allow for a fraction of the required hulls. Simply put, the United States Navy could afford 2 conventionally powered carriers for the price of 1 nuclear carrier. Furthermore, the technological maturity of nuclear propulsion was still in its relative infancy. While Admiral Hyman G. Rickover had successfully championed the nuclear submarine program, surface ships presented different challenges. The 8-reactor plant of the Enterprise was incredibly complex and required a highly specialized, intensely trained cadre of nuclear engineers to operate and maintain. The vast shore-based infrastructure required to refuel and overhaul nuclear surface ships was not yet fully developed. In contrast, the conventional propulsion system of the Kitty Hawk class, relying on oil-fired boilers to generate steam for turbines, was a mature, deeply understood, and highly reliable technology. The global logistical network of oilers, supply ships, and allied ports facilities was already perfectly tuned to support conventionally powered fleets. This debate reached its zenith under Secretary of Defense Robert McNamara. McNamara was deeply focused on cost-effectiveness and systems analysis. He viewed the astronomical cost of nuclear carriers with profound skepticism. He argued that while a nuclear carrier did not need to replenish its own propulsion fuel, it still needed to frequently rendezvous with supply ships to replenish aviation fuel, munitions, and food for the crew. Therefore, the tactical advantage of unlimited propulsion range was somewhat neutralized by the logistical realities of sustaining an air wing. McNamara fiercely resisted Navy efforts to make all future carriers nuclear, repeatedly clashing with Navy leadership and Congress over the issue. This intense budgetary and philosophical conflict is the precise reason the Kitty Hawk class production line was kept open throughout the 1960s. Within the Kitty Hawk class itself, there is a complex development history categorized by different Ship Characteristics Board, or SCB, project numbers. The first 2 ships, the USS Kitty Hawk and the USS Constellation, were built to the SCB 127A design. They established the baseline for the class, featuring the optimized deck layout and a standard conventional propulsion plant. The third ship, the USS America, was built to the modified SCB 127B design. The America featured several subtle but important differences. The most notable was a redesign of the bow to accommodate the massive SQS-23 sonar system. In the early 1960s, the threat from Soviet submarines was considered so severe that naval planners experimented with the idea of giving carriers an organic, active, anti-submarine sensing capability. This modification reflected uncertainty at the time in anti-submarine warfare tactics, not a serious, long-term concept. The America was also built slightly wider than the first two ships. Ultimately, the idea of a carrier using active sonar was abandoned, as the ship's own noise at high speeds rendered the sonar largely ineffective, and the dome was later removed. But the structural differences remained. The fourth and final ship of the class, the USS John F. Kennedy, built to the SCB-127C standard, represents the most radical departure and is often considered a separate subclass. The story of the Kennedy is a direct reflection of the nuclear debate. Originally, the Kennedy was authorized by Congress as a nuclear-powered carrier, designated CVAN-67. The A in this acronym stands for attack, because the Kitty Hawk class was originally designated CVA, or attack carriers, while the letter N obviously means nuclear propulsion. However, Secretary of Defense McNamara flatly refused to release the funds for the nuclear propulsion plant, forcing a bitter compromise where the ship was reverted to conventional power. Because the design had to be altered late in the process, the Kennedy features unique characteristics. The most visually striking difference on the John F. Kennedy is her smokestack. On the earlier ships, the stack was integrated directly into the island, blowing exhaust straight up. This frequently resulted in highly corrosive, hot exhaust gases swirling over the flight deck and into the approach path of landing aircraft, creating turbulence and blinding smoke. On the Kennedy, the stack was deliberately canted out to the starboard, angled away from the flight deck. This effectively pushed the exhaust plume out over the water, significantly improving the safety and visibility for approaching pilots. Additionally, the Kennedy was slightly shorter overall than her predecessors, but featured a modified angled deck and a different arrangement of her forward catapults to launch larger, heavier aircraft more efficiently. She also featured a more advanced underwater protection system and differing armor arrangements. In terms of general characteristics, these ships were titans of the sea. They displaced over 83,000 tons fully loaded and stretched over 320 meters in length. Their propulsion came from 8 Foster Wheeler boilers feeding steam to 4 Westinghouse geared turbines. This system generated an immense 280,000 shaft horsepower, turning 4 massive propellers and pushing these floating cities to speeds well over 30 knots. To operate the ship and her air wing required a staggering human element, with a crew complement frequently exceeding 5,000 officers and enlisted personnel. The true combat power of the Kitty Hawk class was, of course, its air wing, which evolved dramatically over the ship's long service lives. In the 1960s, during the escalation of the Vietnam War, their flight deck was dominated by aircraft that have since become legendary. Fleet air defense and interceptor duties were handled by the iconic Air 4 Phantom, a massive, powerful twin-engine fighter that relied on early radar-guided missiles. Heavy, all-weather strike missions were the domain of the A-6 Intruder, an aircraft capable of carrying an enormous bomb load precisely to a target in the dead of the night. Light attack and close air support were provided by the nimble A-4 Skyhawk. Airborne early warning, crucial for detecting incoming threats and managing the airspace, was provided by the E-2 Hawkeye, recognizable by the large rotating radome mounted above its fuselage. Fast forward to the 1990s, approaching the twilight of their service history. The air wings aboard the Kitty Hawk class had transformed into a highly sophisticated, modern force. The Air 4 Phantom had been replaced by the variable sweep wing Air 14 Tomcat, a dedicated interceptor designed to protect the carrier battle group from long-range bombers using the Phoenix missile system. The A4 Corsairs, an early attack jet, had largely given way to the versatile FA-18 Hornet, a multi-role aircraft capable of seamlessly switching between fighter and attack missions on the same sortie. Electronic warfare and the suppression of enemy air defenses were conducted by the EA-6B Prowler, while the S-3 Viking patrolled the seas surrounding the carrier, hunting for quiet, modern submarines and serving as an aerial refueling tanker. The USS Kitty Hawk herself was decommissioned in 2009, bringing an end to the era of conventionally powered American supercarriers. Today, the United States Navy relies entirely on a fleet of nuclear-powered Nimitz and Gerald R. Ford-class carriers. However, as the geopolitical landscape of the 21st century grows increasingly complex and defense budgets face unprecedented strain, a measured and detailed case can be made for the US Navy to reconsider building conventionally powered carrier in parallel to the nuclear-powered Ford class. This argument does not suggest abandoning nuclear propulsion. Nuclear power remains an absolute strategic necessity for deep water power projection, allowing a carrier strike group to surge thousands of kilometers at high speed without the immediate need for a fuel train. However, the modern fleet faces a crisis of capacity. The Gerald R. Ford class commands a staggering financial premium. The lead ship of the class cost over $13 billion. This enormous capital investment restricts the total number of ships the Navy can realistically procure. Furthermore, the life cycle maintenance of a nuclear carrier is incredibly disruptive. At the midpoint of their 50-year service life, nuclear carriers must undergo a refueling and complex overhaul, known as an RCOH. This process removes the carrier from the active fleet for roughly 4 years and costs several $billion per ship. A modern conventional carrier built to complement rather than replace the nuclear fleet could offer significant strategic flexibility. Such a vessel would not be a step backwards technologically. It could easily utilize the revolutionary electromagnetic aircraft launch system and the advanced arresting gear found on the Ford class. Instead of a nuclear plant, this hypothetical conventional carrier could utilize an integrated electric propulsion system driven by highly efficient modern gas turbines, similar to the architecture used on the British Queen Elizabeth-class carriers. This would of course require significant electrical power generation and careful design trade-offs. The primary advantage of this non-nuclear approach is acquisition speed and cost. A conventionally powered supercarrier could theoretically be built significantly faster and for substantially less money than a nuclear equivalent. This would allow the Navy to increase the total number of available carrier decks. In a global security environment where the United States may be called upon in the Pacific, manage crisis in the Middle East, and maintain a presence in the North Atlantic simultaneously, quantity possesses a distinct quality all on its own. A fleet of 15 carriers, utilizing a high-low mix of nuclear and conventional hulls, offers far more strategic options than a fleet struggling to maintain 11 nuclear ships. Furthermore, the maintenance cycles of conventional ships are fundamentally different. While they require more frequent port visits and a robust logistical chain of oilers to supply the gas turbines with fuel, they do not require the massive, multi-year downtime of a nuclear refueling overhaul. Routine maintenance can be conducted in shorter, more frequent intervals, keeping the ship available for deployment more consistently throughout its lifespan. Strategically, these conventional carriers could be assigned to theaters where the United States and its allies already possess robust, deeply established logistical networks and secure ports facilities, such as the Mediterranean or the waters surrounding Japan and Australia. By taking over these persistent presence missions, the conventional carriers would free up the nuclear-powered Ford and Nimitz-class ships to operate in austere environments where logistical chain is contested or non-existent, maximizing the unique advantages of their unlimited endurance. In conclusion, the Kitty Hawk class were the rugged, reliable workhorses of the Cold War and beyond. They proved that conventional power, when paired with excellent flight deck geometry and advanced air wings, could project immense combat power across the globe. As the modern Navy grapples with the escalating cost and complex maintenance demands of an all-nuclear fleet, the legacy of the Kitty Hawk class serves as a compelling historical precedent. It reminds naval analysts that a balanced fleet, optimizing both capability and capacity, often relies on embracing pragmatic solutions alongside advanced nuclear technology.